All right, welcome everyone. Thanks for the opportunity. It's great to see some folks that I've worked with, and I have incredible war stories to share with some of them. I can see Anil Dongre, Ashlesha, Rahul Chaudhary, Rajat Goel. So it's good to be here. If I've missed out anybody that I've worked with in the past, I'm happy to be in Pune. It's great to see all of you. Like I said, we'll talk about just what RISC-V means to the next generation of compute. I've kept material fairly generic. We've used stuff from the RISC-V International. We are members of that consortium. We back that consortium quite heavily. So I was told that there'll be some students here. So if that first slide that I show after this, it's primarily targeted to a student audience to maybe just clarify what an ISA is. And then everybody talks about, open source. I also want to clarify with regards to RISC-V, what is open source and what is not open source, right? So because that's important to understand. Okay. So first of all, an ISA, is a highly abstracted model of processing hardware. And it basically gives the software programmer a view of what you can do with the hardware, right? So with regards to a CPU specifically, it will document and have, the content of an ISA is an instruction set. When I say instruction set, it documents the instructions. It tells you what the instruction will normally do, what it does under exceptions, and what it does under error conditions. An ISA also documents the registers, the addressing modes, and the data types that you can handle within a CPU. In terms of what have been standard prevalent instruction sets out there, there is a CISC instruction set, which is a complex instruction set. And then there is RISC, which is the reduced instruction set. When you talk about RISC, then you're talking about instructions that typically, and I'm saying typically, are single clock cycle instructions. Of course, over time, to try and match what the CISC architecture can do, people have had to expand out that instruction set to be able to do more. But typically, these are instruction sets that are designed for efficiency, speed of compute, simplicity of programming. Right? So that's what a RISC architecture would be. There are, of course, architectures like VLIW, which is the very long instruction word. You find them in DSP engines, etc. Right? Now, coming to what's closed and what's open. So, if you look at an ISA like either the x86 or the ARM ISA, these are closed to the extent that, maybe some of them are not even licensable anymore, like the x86. The ARM architecture is a licensable architecture. You pay a ton of money to license the architecture if you want to go and do your own ARM CPU. And it's also not one of those licenses that anybody and everybody can buy. They're fairly selective about who can buy an ARM architectural license. Then, within that architectural license, there are, ARM will make its own CPUs. And again, you go and license that for, a certain amount of license and royalty fees. So within the closed ecosystem, that's what a closed ISA would be. Now, in terms of RISC-V, one of the, the myths to bust is that when we say open source, people assume that there is, CPUs out there that you can just go and download the design for. First and foremost, it's only the ISA that is open source, which means that the ISA is developed by a community of developers. And what you do not pay a license fee for is the ISA, right? So you can actually go download the ISA, and if you decide that you want to go and implement a CPU, you're more than welcome to without paying fees to either a consortium or a company for the ISA. And then you go off and design a CPU, and there are companies that have chosen to, in initial representations of their design or implementations of their design, to open source the design also, but that is a choice. That is not the norm, right? So people have access to the architecture, they design the CPU, and then they choose to license it, which is the norm. And then there's a whole community of people out there who are actually doing that. So then you come down to, why a movement like RISC-V? So first of all, just to point out, as much as people are touting it as a modern architecture, yes, it is. but it is built over an experience of over 30 years of compute knowledge of various people contributing to the community. Right? In terms of the the domicile of the technology, and this is the interesting bit, as you understand right now, there's a lot of geopolitics attached to technology. What can and cannot go to certain parts of Asia, what can and cannot go here. I think Mr. Mandekar here, he'll also appreciate the fact that when we try to license technology in India for implementations, you have to sign a lot of end user license agreements. You have to promise that I won't use it for space research, I won't use it for defense, I won't use it for citizen tracking, all kinds of things. And then therefore there are countries, and I think we just have to call out that challenge, where they will restrict the use of technology across the world. So interestingly enough, Switzerland, in its aura of neutrality, the RISC-V Foundation is domiciled in Switzerland. And then, like I said, the aura of neutrality attached to Switzerland means that it is less subject to the issues of geopolitics of technology and what can and cannot go anywhere, right? So the ISA is really open. Anybody can download it with no restrictions of what you do with it. And then it is driven by contributions from members. It's not controlled by any single organization. It does involve a wide community, and I'll address that too. So, if you look at it, in 2015, for example, there were just about a dozen 2017, sorry, just about a dozen members of this community. Today, the community is 4,400 members and ever increasing. Those community members include, fabless semiconductor companies, over 100 of them. There are OEMs and ODMs. There are, large e-commerce companies, or not just e-commerce, just, large internet companies with ambitions around wanting to define their own future with regards to compute that are members of this. There are services companies. There are software companies. So it's really, it's like one of those things. Back in the day, people will say that it takes a village to, bring up a child. This is kind of like that. It's nascent, it's promising, but it does require a community to actually go and build and make sure that everybody's ambitions around next-gen compute are met through a community movement and not by a single company determining what can and cannot be shared with people. If you look at specific industry trends, I guess I have to keep looking at this camera. Sorry about that. So with regards to specific industry, trends in this area, there is an expectation and a belief that, it'll the shipment of the number of units of RISC-V CPUs in designs, will probably hit a number like 16 billion by 2030. And that's great for, a technology that's been adopted, because I think, every one of those numbers matter. I've been at, ARM many years ago, and then they did talk about how many years it took to get to 1 billion units shipped, how many years it took to get to 100 billion units shipped, and so on. I think this is tremendous to say that from where we are today, with maybe less than 1 billion units shipped, to get to the point of 16 billion CPU shipped with a RISC-V core in it. Obviously, I think at the entry level, people are targeting IoT and consumer applications, but the architecture itself lends itself very well to be extensible, scalable, customizable, and therefore it means that people can start to do more with the ISA. And push it all the way up from simple implementations of microcontrollers that can address IoT markets, going all the way up to multi-core large designs with scalable vector engines, cryptography to answer high performance computing needs as well. If you look again, in terms of specific markets and how the expectations are, clearly, consumer is like a consumer electronics, AI in the edge is a big market and a big projected market for RISC-V. The the scalability of the architecture in terms of like I said, adding custom instructions, being able to support it through safety mechanisms, adding security extensions to it, does make it a viable architecture for automotive and industrial applications too. So the 16 billion split that I showed earlier, it largely maps into the markets like this. When you see computing and notebooks, it's interesting to note that there are actually folks in India who are targeting that market, and trying to build compute platforms in the form of notebooks, and or a Chromebook like form factor, using RISC-V CPUs. So I think that's another growing trend, because everybody is looking to build the next gen low cost computing platform, and this is a CPU that lends itself well to that market as well. So let's look at what as much as we spoke about the various markets and the number of units being shipped or projected to ship, it's also interesting to note what people are doing with this, and so this really covers like a gamut of different applications. On the one hand, you have people who are building for the microcontroller market, for simpler applications, just need a simple compute engine. Maybe some of these designs even run bare metal. Some run very simple embedded OSs or RTOSs. And then on the other hand, and then there's a wealth of information for you guys to go and look at in terms of just videos to watch. But there's an incredible one from Meta where you can see what they are doing with the RISC-V CPU. They are building, for example, video acceleration, subsystems, on RISC-V and a custom video accelerator, to the extent that I think almost all uploaded video and downloaded video off of Meta and all the various platforms they own actually happens off of a RISC-V based design. They are also actually doing an inference engine, based on a RISC-V core from somebody, and then eventually trying to push that up to even make it a training engine for AI ML workloads. We have companies like Ventana, who are building very high-end CPUs for the HPC market. And there, like I said, those are the folks who will, extract the value out of the architecture and the extensibility of the architecture to be able to add custom instructions, to be able to define new vector engines, to throw in cryptography, and drive up into the HPC space. All of this, it takes time. Nothing happens in a hurry. You need an ecosystem to support it. You need programmers. You need problems to solve with those kinds of pieces of hardware, and more importantly, more and more compute and the needs of and the sellability of compute hardware also depends on the applications and the software that people are writing towards those kind of applications. And then most importantly, RISC-V is an amazing tech community for everyone, right? So when you talk about countries, it's important to point out that before we talk about even tech sovereignty, it provides a great platform to actually accelerate local innovation and talent, right? So clearly there are people like Professor Kamakoti out of IIT Chennai. There are other institutes who invested heavily in using some of the ISA as a mechanism to get into being able to do CPU design. There are teams at IIT Madras who produced maybe an in-order core. They're working on an out-of-order core. They have then licensed that to at least the tech to other startups who can either use it as is or build on that to do more. So clearly, it's a great platform for to kind of foster talent and grow talent. And maybe it happens at CDAC too, and maybe I'm just not aware of it. Towards that end, I don't know, but it was very interesting to find out that we used to run a program, and I'm not even sure if we still do it anymore, but we used to have a learning platform called the RVFPGA, the RISC-V FPGA. It was a training course, and when I first joined Imagination 3 years ago, the person who ran the university program actually reached out to me and said, 220 colleges in India have downloaded. Can you find out who they are? Right? I'm still trying to discover, who those colleges are. But apparently, 220 colleges did download that, the training program. So it's a great way to learn about computing, and not just computing from the point of view of hardware. I think today a well-rounded and a complete hardware engineer would be somebody who knows how to program the hardware they build, right? So it's great to be able to have a platform like this, to be able to understand what the instructions do, why hardware is designed the way it's designed. So that's definitely one. It does from a again from a country point of view, it does provide access to technology worldwide. To be able to be at these forums, to be at the RISPA International Summit every year, to exchange ideas with people. But most importantly, and then I come back to that first point, it's about tech sovereignty. While as much as I don't want to stress too much about it, it is an issue that will become more and more complex, about every country being able to control what technology it has or does not have access to. And so tech sovereignty is definitely an interesting aspect of it. So for example, quite strangely, if you look at it, EU should have access to pretty much everything that the Western world has, but the EU is at the forefront of pushing the need for tech sovereignty, and what they do out of places like the Barcelona Supercomputing Center. I can see Mr. Vandekar here smiling, and so maybe it's definitely of interest to us as we move through the phases of what we want to do in the area of HPC and supercomputing as applies to a nation, whether it's for weather forecasting, whether it's for anything else, and to be not limited by what you can and cannot do with the technology. In terms of other areas that benefit from it, obviously research consortiums, like I said, today if you have to go and license the ARM ISA, it does. I think it's probably the most expensive license they sell. It's more expensive than buying an ARM core. So obviously that means that if you have to have access to an ISA that allows you to understand what happens at the fundamentals, and then use that in university research programs to be able to eventually customize and develop things that are very specific to what you want to do. Obviously this is another. It's a great platform. It enables innovation, and more importantly, it enables collaborative innovation, because there is an open exchange of ideas in all of these forums. For startups, it's great. Like I said, there are people who have chosen to open source their design over and above the ISA, which means that access to technology, can be fairly easy. For startups, it's also great because the choice is huge. It's not like there's one vendor out there having a monopolistic, control over the technology. There is many different shapes and sizes of the CPU to choose from, and that just makes it so much easier for startups with limited funding, with no option of getting it wrong at all. So you're just getting first-time right designs. It's great that there's a community out there that can support startups with very directed intent. If you look at what's the challenges of consumer and industrial markets. First of all, consumer and industrial markets are very cost sensitive. All right. So everybody's focus is primarily on area. area drives most of the cost of silicon. And then, of course, there are, then there is, the efficiency with regards to power and maybe performance, at least in the consumer world, that's the last of the considerations. Then when you talk about, and again, since you're talking about area, you're saying that obviously you want to extract maximum performance, per millimeter square of area on silicon. And so, if you look at uh, the designs that are out there, while they do, the companies that have designs that maybe, map to this, these are not, sufficiently modern anymore, not necessarily extracting maximum value of changing architectures with regards to, memory. They are not necessarily tied in closely with, accelerator blocks that you would like to add into your design. And then, so therefore, those, that's, performance increasingly comes with an increasing cost, right? And I think that's something that the RISC-V design can satisfy in terms of providing a new method or a new architecture towards computing and taking and like I said, this is not simply a bunch of people that are proposing something new today, but having understood problems over 3 decades, they are proposing solutions that are definitely scalable all the way from extremely area sensitive, power efficient, all the way up to performance and performance driven designs. Okay, so and then now when you come to like a entirely new ISA, I think the biggest challenge, is around, what's the community that's available to support you. So even if you look at, IP, so you have a CPU, but CPU is not the end of the world. You're out building an SoC. You are looking for third-party IP. You're probably looking to build some IP yourself, right? So then it comes to the question of standardization of interfaces, standardization of IP out there. So clearly there are challenges in that when you're trying to work with an entirely new ISA or an architecture that's different. But I think there are ways in which people are solving that. People are using accepted industry standard interfaces with regard to hardware. The bigger challenge is, with regards to the programming, ecosystem and the software ecosystem out there. So there is this large movement inside of RISC-V. It's called RISE. RISE is the RISC-V software ecosystem. And I think, one should not, as much as we talk about a CPU architecture, one should not overlook the importance of, what RISE means to the overall software, to the overall RISC-V ecosystem, because, without a good supportive software ecosystem out there, if you don't have, a path to constantly, staying, at pace with what's happening maybe with the Linux Foundation, if you don't have, the ability to stay on pace with what's happening with, Android, and many other OSs out there, it could be, RTOSs like, ThreadX or whatever else that you have out there. If you don't have that, programmers comfort, then, you're just building hardware that, has to survive on its own. And then that doesn't really work. So I think, you've really got to have a large, like I said, a family of people out there supporting what we're doing from a hardware point of view. So, I having touched upon, like I said, the intent of the larger consortium, maybe I will, and for the moment, ignore our logo out there. I'm still going to say that, these are, thoughts and challenges that, one needs to tackle from specific market segments. So I will talk about automotive a little bit. I will talk about, AI/ML a little bit as we go through this. So, in automotive, I think everybody now talks about a software-defined vehicle. So, it's more and more, it's about the software, right? The CPU and all of the, hardware systems out there, are only enabling what you can and cannot do, with a vehicle. There are people that, will say things like, okay, nowadays a car is like a mobile on wheels or whatever else it is. But, it is really about the software ecosystem. But before you get there, there is still, there are pieces of hardware that you have to, tackle. So first and foremost, it's performance, right? So you need to, address performance from. So let's see how, compute hardware is used in the automotive space. Right? Compute hardware can be used for, IVI, which is, in-vehicle infotainment. It is used in HMI interfaces. It does get used for ADAS, and ADAS, is not like an all-encompassing word. There are various levels of ADAS. It could be just driver assistance to all the way doing autonomous. And then there is, and there are AI ML workloads. So clearly you are looking for, the last thing that maybe an automotive company or an OEM wants to do is to have, maybe three different architectures supporting, different parts of what the vehicle can do. So therefore you do need to have a scalable architecture that will say, okay, I can address IVI and all the way up to maybe, eventually an autonomous driving vehicle. So clearly performance is key. Obviously, then, you come to efficiency. Efficiency comes from the fact that, while there is a push towards EV, or a hydrogen fuel cell, or a battery operated, full EV, then obviously you're saying that you want efficient computing. You don't want power hungry computing, sitting in the trunk of your car, sucking up your battery. So, efficiency is definitely, a measure of what, you require. So efficiency in the form of both power and area. And then, in the automotive space, obviously, maybe some of the most important things are, the three things that you see at the bottom. Strangely, that's one of the parts of the organization that I'm responsible for, which is quality, functional safety, and then cybersecurity. These are quality is more from an external certification to make sure that organizations are certified. But I think where you really come down to product level certifications, that's where it becomes really tough in the automotive space. These are not easy certifications to get. There are standard auditing companies out there. And again, like I said, I've got teams who can maybe get into more detail about what needs to be done to make hardware functional, safe, and capable of being used in automotive designs. But over and above having done all of those, some of the tool chains to maybe able to first self-certify itself are reasonably complicated. Over and above that, you need to be able to bring external bodies in to certify. So they will run through some sets of workloads or a fairly detailed audit process to be able to certify your product, to say that it's okay, I guess somebody's prompting me to move on, but so and then therefore you will so there are ASIL certifications. So there's an ASIL B, ASIL D. You need to be understand what level of the market that you're trying to get into, and then of course there is cybersecurity. Which means that the last thing you need to do is to be in a vehicle and have somebody else outside, a bad actor being controlling what you are doing inside the vehicle. So cybersecurity is another area. So these are all the real care abouts from an automotive point of view. Obviously some of it is hardware supported in terms of making sure that you have, maybe fail-safe hardware, you have sufficient protection on compute subsystems, on memory, but at the same time, there's a huge bunch of software out there that needs to be able to run and run in a manner that is secure. So security is a big thing in automotive, as much as it is in some of the consumer applications as well. But security is a key driver for the automotive world. And then again, just ignore for the fact that it might look like, there is a little bit of, company specific information here. I think, when you get into the automotive space, I think you've got to understand that you've got to have a development life cycle that has stood the test of time, understands what it takes to develop automotive product. Quite interestingly, for anybody who's interested, our automotive GPUs are done out of our team in Pune. So that's a team that understands what it takes to design, verify, and validate automotive grade product. And then obviously, in the automotive space, again, we look at the automotive problem more as a heterogeneous compute problem. It is not purely, I need the biggest CPU that can do the fanciest thing. It is really solve for function and for purpose. And very often, therefore, in the automotive space, we are mating a CPU with a GPU. The GPU could be like, for general purpose compute, or it could even be for rendering graphics. So if it's general purpose compute, then, clearly it's for targeting some amount of AI ML workloads to run. If it is rendering graphics, then it is for IVI and for HMI kind of applications. In terms of AI and RISC-V, we believe it's a great match. So what's really happening in the AI and AI space? So we've called out flexibility. There are people who keep touting different number formats. All right, and sometimes to change number formats in current existing ISAs becomes fairly complex. I think the AI, the RISC-V, the body and the consortium has been very cognizant of the fact that there are people who are constantly experimenting number formats. So which means, you have the, somebody says, I need like a B float 16. Somebody says, okay, I need, floating point 16, but I need integer 8. I need floating point 8, I need integer 5. So people keep experimenting with different, number formats. We've got to be able to have an ISA that can deal with the flexibility of number formats and being able to quickly turn around, new instructions and new ways of being able to do compute. Obviously, configurability is a big thing. And like I said, you've got to have something that's configurable and scalable. You could be solving, a problem as simple as maybe like a smart doorbell with like imaging. But on the other hand, there are people who are pushing all the way up into, saying that maybe I will even build training engines. So I think from that point of view, it is very, very scalable. Collaboration is another big angle with regards to AI and AI workloads. Keep in mind that no one company, maybe save one, and I don't want to name them, has a complete story with regards to, what you can do on AI. There are, there's hardware, there's many, software frameworks out there, whether it is, to solve for the graph, to reduce the graph, to eventually compute, I think, so you just need a big, ecosystem of tools, frameworks, and hardware, supporting hardware to be able to run AI workloads. So in terms of some simple examples of what can and cannot be done, and like I said, this really covers everything. For example, wake word detection. That's like the what everybody knows as Alexa do this, Alexa do that, or Hey Siri. So clearly, you just need a small real-time embedded CPU with the capability to do some, vector and matrix computations. You look at AI for a smart doorbell. You're saying that I need like the small RISC-V CPU with like a image, sensing processor, or like maybe a GPU. You then Obviously, people are doing some amount of AI workloads on mobile phones. It's like a combination of CPU, GPU, and a neural processor. And then as you get more into, and then so these are examples of maybe doing AI at the edge, and then there's inference in the cloud, but of course that needs pretty significant network infrastructure, and then there is data center training. So all of these are workloads that lend themselves to a computing architecture that, like I said, the mantra is it's got to be scalable. It's got to have, it's got to support and enable innovation. And more importantly, it's got to have a community out there that can collaborate and deliver solutions together. Like I said, it is very difficult for, somebody to say that I can do it in isolation. In terms of, okay, there are a few slides that I'm just going to throw in about us. But like I said, we've been a fairly new entrant into, not into CPU design, but specifically in our participation on RISC-V CPUs. It's interesting to note that when you are out there, asking customers to maybe consider your CPU design, there are a number of customers and important ones who actually, among other things, will ask, they say they're fine, okay, with your, PPA metrics, my CPU can do this. I think many of them ask, but what do you do towards the community? And that's like a big question that people ask when you're involved in the RISC-V space. It is a key concern. It's a key ask of customers in terms of, how do you contribute to the community? What do you do towards the community? And therefore, we have, in certain aspects of RISC-V invested in, maybe participating. I am, again, like I said, I'm not here to call out people's names. I'm just saying that, should you ever decide to, go off and try and attempt to do something in the RISC-V space, this is important. And therefore, for those of you who may not know, even I think our own Ministry of Electronics and Information Technology is a member of the RISC-V International, and in their own way make contributions towards the consortium. We are also a founding. I spoke about RISE, which is the RISC-V software ecosystem. There's as you can see, it's not just us. There are a lot of big names over there who contribute towards the RISC-V software ecosystem as well. Again, I think I spoke about the fact that it's in modern day compute, it's not only about the CPU. It's about everything coming together. I've talked about the CPU, GPU, and AI compute, but that's just the hardware part. There is a whole army of folks out there building software and software libraries. There are tools that go with it in terms of profiling tools, debuggers, and this is where the community comes together. And then, if you want to specifically target industrial, automotive, and other applications, then, functional safety and security is another big angle to it. So it's about really all of this coming together to make RISC-V a meaningful new architecture for the future. Before Apurva gives me dirty looks, like I said, I won't spend too many minutes on that. We've got like a few products. We've got like one. It's a fairly modern design. It's a power efficient in-order CPU that we call the APXM 6200. It's the second design that we've done. We've done a real-time core. Again, our focus on that has really been about performance density, about making it easily integratable with other IP out there, whether it's our GPU, somebody else's GPU, other IP. We've also, focused a little bit on, we've got to face the reality that there is a dominant architecture out there today. So we focused a little bit on ease of migration from ARM-based designs, and of course we've built a compliance tool that helps us to demonstrate compliance against RISC-V profiles. Where you could use them is you can use them in digital TVs, machine vision, wearables, smart speakers, etc. And I think we've spoken about performance sufficiently, but when it comes to trust and security, there are trusted execution environments, TFA, different methods to tackle security and trusted execution environments. We've taken a simple approach. I think it's quite popular. Trust zone is one of the more popular ways to approach security. So we've just come up with our own method and means of being compliant with that. So that's really all I had to say today. If you have any questions, I'm happy to take them along with everybody else who can support me. I should prepare first.
So basically, it's like a ecosystem, right? Like which number said, we have a hardware and then software, right?
Right.
Now we are calling it open source, right?
Right.
So any of these components can US government ban anytime.
No, sorry, sir. So first of all, they don't, obviously, if somebody goes and builds a CPU in the US, right, the government, right? But keep in mind, the implementation is not open source, right? The CPU design is not open source. The CPU, the ISA is open source. And the ISA, like I said, it's not domiciled in the US. The ISA is domiciled, like the ISA International is domiciled in Switzerland. So the ISA will always be available to anybody, right? So which means tomorrow, if some XYZ company in the US says, no, I'm sorry, I can't give you my CPU. Obviously, you can then go find somebody else somewhere else, or push comes to shove, you can always design it yourself. And so the tech from an ISA point of view, is open, it's safe, it's available anytime. The implementations will depend on where the IP was created or designed.
Okay. What about the software framework? Is it coming from open source?
So again, so RISE is a community that defines, at a broader level, how certain problems can be tackled and solved. Okay. Now, RISE may create certain specific problem areas, and people within the community can pick it up and solve those problems. Right? Now, you may contribute back those, the contributions that you make, and they could go into various different forums. For example, Google is quite active in the RISE forum in terms of calling out what problems need to be solved. Right? We've been quite active in responding to those problems and trying to fix them. But I think and all of those will be protected under the notion that you're contributing back to RISE, which in itself, is open source and available to everybody. In fact, since Vamshit again, one thing that comes to mind, even in the way we validate and verify our CPU, it's quite interesting. We use one licensed tool. Okay, we use a licensed a random instruction sequence generator, but we also use an open source, right? But the open source one, is something that you can build on. The licensed one, we buy from somebody, and they make changes and tweaks to it as the ISA, advances. But it's a mix of, you can license some parts, you can build some parts yourself, you can work with the community on some. Right? So the open source tool that we use as a random instruction generator, not all of it is built by us. Right? We take what's there and you build on it. Right? There also maybe you are compelled to contribute something back, and some you can hold back also. So it's complicated.
Yeah, got it. Thank you.
Thank you for a very wonderful presentation. So my curiosity is that, let's say, how smooth or how seamless it will be, let's say, if it is a software application or an operating system with a good threads, if I'm jumping in embedded application, then this will run on a different processor and then more migrate to something that's risk-based and then risk-based, and then how smooth that transition can be, especially if it's operating, we need not be, this obvious to the hardware. How smooth do you think that it is?
Do you want to take a shot at it? Yeah.
The second is that it's the open source objects, instruction object, a different set of architecture problem. Processor itself that come up. So which means that one software is developed targeting to one risk five ecosystem. You can be aware about different risk five. How smooth that will be? Something that I would be. That's
How smooth is software migration
Yeah.
from one CPU architecture to another?
No, one risk to another.
that's the second question.
For second question, yeah.
Just for example, if you're having an ARM-based SoC and you want to move to a RISC-V based code, right? One of the things which we do is we actually give a porting guide, right? Both from a software point of view and hardware point of view. And how do you port from a ARM-based SoC to imagination-based one? And some of these software guide, for example, the compilers and all, they're all open source. Today, when we release those things, we actually release those compiler SDKs. You can go to Imagination website today and download them. So either through Rise or through Imagination, there are enough tools available for you to, migrate. But yeah, it's not going to be like a plug and play. It is going to take some time, and that's why when the software stack is getting heavier and heavier, for example, in a mobile device, when you have a big CPU, mid CPU, small CPU, having the coherency through software, hardware, it gets complex as your stack is heavier. But whenever people are developing the RISC-V CPU, they are giving those porting guides and software guides help you with that. And between RISC-V processor to RISC-V processor, if you are still, like for example, there is a compliancy suite today which is developed for you to run on your RISC-V processor, and you will be able to run that and see if this RISC-V works, and then the same software stack should work on the other RISC-V if you are compliant. And there are some extensions which are specific to your processor, and there are some custom instructions again which are specific. So there you might have to.
Well, I will agree, but let's say if we're putting a different architecture, this latency will come into picture.
Sorry to maybe take this.
Yes,
Okay, fine.
We are almost there.
Sorry.
No, we can take another question, one, maybe last one, and then we can.
Yes.
Another opportunity.
Sure.
I'll
call out your question for everybody.
Yeah. The question is like automotive and HPC, right? As the demand, now it is like almost, it is the same amount of compute HPC data center requires and ADAS port requires. So I think the key problem is integrating of multiple, because GPU is essentially small code, but integration is the key of building that horsepower and giving those many GPU or cores internally for the workload to distribute.
Correct.
So how or what technologies are primarily helping this integration, allowing like multiple cores getting integrated and allowing that workload.
So if you really go okay, so I think the question is that the problems of automotive when you're doing ADAS for versus like doing an HPC implementation are fairly similar. You need large multi-core designs. What's out there in terms of helping integrate these designs. Before answering that, the one difference that will always exist between HPC and automotive is that there is a plug in the wall for HPC and there is only a battery for automotive. So somewhere along the way you still need a power efficient design. But that said, if you're talking about multi-core, that's a problem that's been solved, because that's less of an issue in terms of people are out there building clusters which are 4-core, 8-core, multi-cluster, multiple memory levels of memory hierarchy, going all the way. In fact, I've seen somebody even touting like a leave alone L3. I've even seen people having level 4 caches. So I think to be able to do multi-core design, I think there's enough fabric out there to be able to connect large, arrays of, cores, right? So which means that if you want to push to 64 cores, 128 cores, those kinds of fabric exist, right? The issue is that, you just have to make sure that your CPU design, has interfaces that can then integrate with a fabric, even if you're not designing the fabric yourself, right? So, you could, I think I've seen some folks, for example, doing a multi-core design that uses maybe some of the fabric interfaces that even ARM has. So even though it's an ARM interface, they've done some custom variant of that, and then there are people doing that. So I think, that's a lesser of a issue in terms of how do you do large multi-core design. But I'd still separate out the problem for HPC and automotive and say that one runs off a battery and one runs off of a wall socket. So there are still differences. Yeah. Yeah.
All right, thanks. Thank you.